Right. So let's see. Yeah, I think we can probably start now. So it's my pleasure to introduce today's speaker, DG. So D is a PhD student at MIT. He is in his 5th year and graduating soon. And his work focuses on NLP and its application, specifically in biomedical and health informatics domains. So his work has focused on sequential sentence classification, transfer learning for low resource languages. And he has also done some work on adversarial attacks and defense in NLP setting. So he also has done some work on text generation. So actually, this is how I came to know him. So he did an internship at Amazon, I think last summer, right?
Yeah.
And so the internship was Shuyang Gao. So many of you might remember Shuyang. So he was a PhD student in our group. And Shuyang had very high, recommendations for this. So we decided to basically set up this interview talk. And so now here we are now. And Dee, please, you can take it now and start talking about the presentation.
Mm-hmm. Sure. Can you see the screen now?
Yes.
Okay. Thank you for the introduction of myself. So today's presentation, I will present my research on the transfer learning for language understanding and generation. So I'm from MIT. Most of the background of myself has been introduced by Aaron, so I don't want to elaborate more. The last thing I want to mention is that my advisor is Peter Solowitz. So our group is working on the healthcare AI and clinical decision making. So let me proceed to the research of my previous projects. So I have been working on the natural language processing in the last several years, and I want to divide my research into 3 directions. So my first direction is for the transfer learning. For this direction, I have been working on 3 different tasks: the sequential labeling, multi-choice question answering, and machine translation. So for this direction, my main goal is to improve the performance of the low resource data or task by transferring the information from the high resource domain data. And the second direction of my research is the text editing or rewriting. So for this direction, I have 2 works. The first one is about the style transfer. More specifically, I work on the sentiment and formality manipulation. That means I can change the sentiment or formality of a text without changing the semantic meaning. And the other work is about the stylistic headline generation. So that means that based on the plain and factual headline generated from the articles or news, I can insert some styles into the headlines so that they can be stylistic and more attractive to the readers. So for this direction, the main goal is to rewrite the text into the new format or style without changing the content. And finally, for the third direction, it's about the robustness of the deep learning models on the NLP. So for this part, I have both directions for the in the reverse side. One for the adversarial attacking, and the other is on the reverse side about adversarial defensing. So both subdirections contribute to examining and improving the robustness of the deep learning models on NLP. So this is a summary of my previous research. So today, in this presentation, I will focus on the first direction to talk about the transfer learning used for two tasks. One is for the language understanding, the other is for language generation. So first of all, let me introduce the first work. For language understanding, my main task is about the multi-choice question answering. And so what is the multi-choice question answering? So for this task, we are giving the input of one context. It can be a snippet of the document or dialogue or several stories. And then given the context, we have several questions. For each question, we are giving several answers so that we can pick one of the answer as the correct answer to the question. Then the model is required to pick the most appropriate answer from the list of options. So this is the kind of high-level introduction of what is the multi-choice question answering. So as I mentioned, the context can be in many formats or types. It can be a long story or long document from the Wikipedia. And the question can be in any kinds of types. So given the various types of the question natures, we see that this kind of task is very difficult, since in order to solve those questions, we need the models to acquire a lot of advanced reading skills, such as the logical reasoning, the common sense reasoning, and some capability to summarize a long document. And the model may even need to solve some equations based on the arithmetic capability. And finally, the model needs to do the inference between the language snippets or text. So given this kind of challenging task, we need to find out several data sets to benchmark our model or methods so that we can see whether our method is better than the previous one. So the first benchmark data set we have tried is this kind of new, very recent data set. It is called multi-choice dialogue-based reading comprehension examination. The short name is the DREAM. So this corpus or dataset is connected from the English examination in China. And in total, there are 6,000 dialogues, and each dialogue is multi-turn at a multi-party, and they are connected from the daily life. Each dialogue is associated with several questions. So in total, there are 10,000 questions, and each question have 3 options. One of the question is correct, and there's only one exactly one correct answer. So this is so we have talked about the data set we want to use. Then I want to introduce the main architecture or model that we want to use to tackle this kind of problem. So this is the figure to illustrate the model that we want to use. So it is based on the transformer or BERT architecture. And so we are given several options for each question. So we need to first concatenate the passage or context with the question and with the one of the options together into a long sequence. And then we input the sequence into the BERT model to get the hidden representation vector so that that vector can represent that long sequence. Then we can use a certain kind of classifier to map that high dimensional vector into a single value that can be acting as the logic value. So for each option, we will have one single value to represent the probability of whether this kind of option can answer the question. And then for n options, if we have n options in the list, then we will have n values after the classifier. Then over the n values, we will use a softmax to convert those n logit values into the probability vector. And in this case, each value can be acting as the probability value. And the summation is 1. Finally, for the prediction of the correct option, we will pick the option with the highest probability value. So this is for the model part. How can we encode the input and get the final option out? And our contribution in this work is based on this kind of architecture and explore the use of the transfer learning and see how transfer learning can improve this kind of basic model. So since we want to explore the transfer learning, then we will proceed to the next question. The key to the success of the transfer learning is that we need to find a good and appropriate source datasets. And for the source datasets, we have two kinds of datasets to consider. One is the in-domain dataset, and the other is the out-of-domain dataset. So for the out-of-domain dataset, since it can be irrelevant to the task we want to tackle with, there are many choices we can choose. So how can we find the most appropriate one? In order to do this, we need to explore or get into the data we have and see whether we can get some hint from there. So I examined the question types in this dataset and categorize them into several types. First of all, some questions in this dataset ask about how does the woman like this movie. So this question is kindly asking what is the sentiment of this person towards something. So it is very like the sentiment analysis problem. So it came to me that maybe the sentiment analysis dataset can be a good source of the knowledge to learn from. And for the second type, in some data, we are seeing this kind of example. Say the evidence sentence for the correct answer in the context can be, I want to hang out for a good movie. And the question is, what does the man mean? And the correct answer is, he wants to see a film. So the evidence sentence in the context and the answer can form a pair of the paraphrase. Then it came to the conclusion that maybe the paraphrasing dataset can help us to solve this kind of paraphrasing problem in the questions. And finally, we have this kind of example. Say the question is still the same, what does the woman mean? But the evidence sentence is like this. Yes, and if I had just used my head, I would have it figured out. And the answer is, she didn't think carefully about the problem. So here, in this sense, the answer is not a direct paraphrase to the evidence sentence, but it is kind of entailment relationship. So this question may require the model to have some language inference capability. In this sense, so the language inference datasets can be very helpful to augment our model. So in this way, we can figure out what is the maybe appropriate or potential out-of-domain datasets for the transfer. And next, we consider the in-domain dataset. So for in-domain dataset, we just need to find out what is there in the same domain. Do we have any kind of data in the same domain? So we find out there is a data named race. So it contains 100,000 questions in total. It is also connected from the English examinations in China. And the only difference is that in this data set, all the passages or context is the documents. It's a long document. While in the dream data set, we have a lot of, we have the dialogues as the context. And for the other things, these two data sets are very similar. So in this case, we can use this kind of data set as the in-domain data set. So in this table, we summarize the results of the first explored transfer learning setting. So that means we first train or fine-tune the BERT model on the source data sets that we have chosen. Then we further fine-tune it in the target data set, the dream data set. As we see from this table, in the first row is the baseline. That means that is the development set accuracy that we directly fine-tune the model on the dream dataset without doing any kinds of transfer. Then in the succeeding rows, we show the experimental results by transfer learning. So first of all, we can look at the first blanket. We see that by transferring or first fine-tuning on the sentiment analysis dataset, and further on the dream dataset, we will see even worse performance compared with the baseline. So that means the sentiment analysis is not helpful to our transfer. And next, for the paraphrasing, indeed, the paraphrasing dataset can give us a marginal improvement over the baselines. It seems that it can be helpful, but not that helpful. So next, we also tried span-based question answering dataset. So span-based question answering dataset is also about question answering, but instead of the giving the multiple choices, the answer is in the format of the spans. So that is a span of text in the original context. So in this kind of out-of-domain datasets, we tried several very popular datasets. It's the SQuAD 1.1, SQuAD 2.0, and MRQA. The MRQA is a recent released dataset. It is a mixture of many large span-based question answering datasets. However, as the results turns out, for this kind of out-of-domain datasets, only the SQuAD 2.0 can give us a little improvement, and the other two types can make the performance much worse. So it leads to the conclusion that although the span-based question answering is very similar to our target dataset or targeted task, they are still not that helpful or even make the task worse. And next, we have tried the natural language inference datasets. For example, we have tried the multi-ALI and SLI, and even a mixture of many ALI datasets from the GLUE benchmark datasets. And all of them can contribute to the improvement of the performance by a lot. So in this case, we see that the ALI is really helpful to our target dataset. Finally, for the in-domain datasets, the race dataset, we can see that the improvement over this kind of dataset can give us the most improvement. So we will have the following two takeaways from this kind of experiment results. So first, transferring from the in-domain datasets, the race datasets can help the most. And second, for the out-of-domain datasets, the ALI datasets can be very good out-of-domain datasets for our target domain, target stream dataset. So here is the question next. how to combine these two kinds of out-of-domain and in-domain datasets so that they can contribute together to the improvement. And we have tried this kind of new method, that is the multitask learning and multi-stage fine-tuning. So next, I want to show some experimental settings to illustrate or detail this kind of method. So this is the table that shows the results by various kinds of settings of transfer learning. I can explain it row by row. So here for the first row, we still have the baseline. That is the without any transferring, just fine-tune the bird model on the target dataset dream. And for the second row and third row, we have shown that by first fine-tuning on the model on the NLI and the race datasets can give us some improvements. Then we proceed to the fourth row. So comparing the third row and the fourth row, I mean the setting 3 and setting 4, we see that instead of fine-tuning the model on the race and then on the dream, we can try multitask learning the two in-domain datasets, the in-domain datasets and the target datasets together, so that the improvement is actually much better. So in this case, we learned that for the in-domain dataset with better multitask learning and try training the in-domain datasets and the target dataset together instead of the two stages of fine-tuning. And based on the results of the row setting 4, we want to further insert the NLI dataset. So how can we do that? So we have tried 3 settings, 3 different kinds of insertion methods. So for example, for the setting 5, we can do the fine-tuning in 3 stages. First on the NLI, then on the race, then finally on the target dataset dream. But the result turns out that it's very bad. So that leads to the conclusion that we cannot fine-tune the model on too many stages. And then we can look at the setting 6. So we can also multitask the 3 datasets together instead of doing the 3 stages of the fine-tuning. And this kind of multitask learning can be better, a little better than the setting 4, but not that better. So in this case, we can see that by doing the multitask learning, the NLI dataset is not beneficial very much. So finally, we came into the setting 7. So instead of doing the multitask, we can first fine-tune the model on the NLI and then multitask learning the race and dream together. So in this case, the improvement over the setting 4 is much more obvious. So it came to so by summarizing this kind of experiments results, we have this kind of conclusion. So that is, for the transfer learning, we can start from the pre-trained model first, and then we do the first stage of the coarse tuning. So that means we can fine-tune the model on the out-of-domain datasets first, and then proceed to the stage 2. We fine-tune the model further on the combination of the in-domain dataset and the target dataset together using the multitask learning. So that means we can divide the fine-tuning by 2 stages, and the final stage would be a multitask learning. So this is the multi-stage multitask learning strategy. So having talked about our explored transfer learning strategy, we will come to the final 2 points of our contribution in this work. So the first one is about the multi-step attention network. So here, in the previous results, in the previous experiments, we used the MLP as a classifier. That is the multi-layer of the feed-forward neural network to map from the high dimensional hidden vector encoded by the BERT model to the final logit value. But instead, we can use this kind of attention network. So I will not go into the details of these equations, but I want to describe the method in a high-level concept. So we do calculate the attention between the encoded representation for the passage or context and the representation for the question option pair. And we calculate the attention between the two representation vectors so that they can attend to each other. And then we use this kind of attention scores to aggregate the passage. So after doing the aggregation, we do multi-steps of the reasoning using the RI unit so that our aggregated score as the query can be made better and better. And by doing this kind of multi-step reasoning, we can make the attention scores better than the last iteration. So the final logit value will be based on the attended vector from the passage and the question answering pair. So by using this kind of multi-step attention network, we can see that it can give us certain kinds of improvement. So in this figure, the 0 means that we don't use this kind of MAN network. And by using 5 steps of reasoning, we can bring in about 1.5% of the improvement. So that is about the attention network. The next thing is about a very simple surgery to the original data so that we can gain some kinds of obvious improvement. So this kind of surgery is named as speaker normalization. So as we look into the data, we will see that in the data, there are many dialogues like this. So each utterance starts with a speaker name. Then the speaker name usually has the formats of the W and M. So the W means the woman, M means the man. However, in the question, we always have this kind of question like, what does the man mean? So question is asking about the information from the man. However, in the utterance, in the dialogues, we don't know which one is the man or which one is the woman because the man and the M is not corresponding to each other by the model itself. So we need to complement this kind of missing information and insert it into the model. So how do you insert this kind of information? We can just replace the M with the man in the original data and W with the woman in the original data. So that in this case, the model will implicitly know that the question is asking about the information from the utterance from the man. So this result shows the improvement brought by the last mentioned 2 changes to the original model. So the first row shows that what is the accuracy we have obtained from the transfer learning. And then we add the speaker normalization, and that gives us 1% improvement. And then we replace the MLP classifier with the attention network, and it will give us another 1.4% of improvement. So this table shows the final results of our mentioned the previous various kinds of changes. So we named our method as the M triple. So that is the multi-stage, multitask learning, transfer learning. Here in the blue line, in the results marked by the blue line, we show the baselines of using various kinds of bird models. We have tried the bird-based model, the bird large model, as well as the Roberta large model, and report the results of their accuracy by fine-tuning on our target dataset. And then we augment this kind of basic model with our proposed method and show that show the results coded by the green lines. And as we see, the numbers in the brackets shows the improvement of our method compared with the baselines. And as we can see, the bird-based model can have the over 9% of the improvement. And for the Roberta large, we can have around 3 to 4% of the improvement. And the best accuracy we have achieved is very close to the human performance. That is shown here. So after describing and our results on the first benchmark dataset, we further extend our method to other benchmark datasets for the multi-choice question answering. So in this table summarizes the statistics for the 4 datasets we have tried. Besides the DREAM, we also tried the MC test, SumEval 2018, and TOEFL. And especially for the TOEFL, it's very small. The total number of the questions in this dataset is less than 1,000. It's much less than the other datasets. So this table shows the results of our methods on the other benchmark datasets. So still, we first report the baseline methods performance in marked by this kind of blue square. And then we report the results of our method compared with the baselines. And still the numbers in the brackets shows the improvement of our method compared with the baselines. So there are 2 things we want to highlight. So first of all, the MC 160 and MC 500 is coming from the same datasets, but in the official split, they split it into 2 parts. One contains 160 questions, and the other contains 500 questions. 500 passages. So they actually very similar to each other, but only the size is different. But we can see that our improvement brought by our methods is even more obvious in the smaller datasets in the MC 160 compared with the larger dataset, the MC 500. So that gives us the conclusion that the transfer learning methods is actually more effective on the smaller datasets. And another thing to highlight is that our best performance, the best achieved accuracy is actually very close to the human scores. So finally, for this work, we want to show that our proposed method can also benefit the source datasets, the in-domain dataset, which is the race dataset. So this table shows the comparison. We first show the accuracy or the performance achieved by the bird-based model, which is the baseline. And then we add several modules that we have proposed. For example, we can first fine-tune on the NI, then on the bird-based. That can give us some performance improvement. Or we can also transfer from the DREAM dataset, although it is much smaller than the race. And also we replace the MLP classifier with our proposed MAN, and it also leads to some improvement. So this is the results that overall, what is the improvement of our methods over brought into the source dataset. So still we first report official scores achieved by the various kinds of bird family models. And then we add our methods onto those kind of baselines, and we achieved around 2 to 3 kinds of percentage of the performance improvement. So this is for the source data set. Yeah, so overall we have talked about this kind of work on the by using the transfer learning on the language understanding task. So next I will proceed to the language generation part. So for this,
I'm sorry. Can I ask a question here?
Oh yeah.
So do you have case studies showing that what kind of questions could be answered correctly after you use the source data set, while they were not answered correctly before they used the source data set, and also to verify whether that performance gain is brought by the source data set?
I do have the results in the backup slides. So we do have an error analysis on the data. So here we first randomly extract the 150 wrong samples predicted by the bird-based model. And we use the human annotation to categorize all those wrong examples into the several types. So we analyze them into 2 major types, the matching type and the reasoning type. Matching means that we can get the answer by directly service words or keywords matching. The reasoning part means that we need to have some kinds of reasoning to get the answer. And we also have divided them into subtypes. Say for the matching, we have the keywords matching and the paraphrase matching. And for the reasoning, we have the arithmetic reasoning that is doing some equations, and also the common sense reasoning and for others. So these are the percentage of each type. Of course, we have another kinds of categorization. So the single sentence means we only need 1 sentence from the context to get the answer. And for multiple sentence means we need at least 2 sentences to get the answer. And the whole dialogue means we need to summarize the whole dialogue to get the answer. So after doing the categorization, and we then evaluate our best model on this kind of 150 wrong samples and calculate what is the accuracy for each subtext. So here is a table to show that the accuracy achieved in the matching types is very high, while the reasoning type is a little lower, especially that our model cannot solve the common sense questions very well.
So I see there are further questions. So if it's John, specifically, it seems you have a question. If it's a clarification question, please go ahead. Otherwise, let's just proceed with the talk and you can ask the question later.
Well, yeah, the clarification question just on this slide, the best model, that's the Roberta Large model that's then been adapted, right? It's not the BERT-based model?
Yeah, so we haven't tested, at least in this result, we haven't tested the BERT-based model augmented by the transfer learning, but we can try that and report the new results. It is a very good suggestion. Okay, I will proceed to the next one. So For the language generation, I have tried to work on the unsupervised domain adaptation for machine translation. So first, I want to introduce what is the unsupervised domain adaptation for machine translation. So as we all know that the neural machine translation has achieved a lot better performance compared with the conventional machine translation models, say the statistical ones. But they do require a lot of, or a large quantity of the parallel translation pairs as the training data. And in some cases, actually in many cases, in order to have a very good performance of the model, we need to have millions or tens of millions of high quality translation pairs as the training data. It's actually very realistic for the low resource data. So we need to also consider, say, what about for the low resource domains like the medical, IT, or any kinds of domains that have very low resource data for us to train. And we also have a lot of language pairs that are low resource, and we cannot find very large quantity of translation pairs. For example, for the English to the Vietnamese. And for the low resource, and also in many real applications, in the many very specific user cases, we are facing a lot of low resource problems. So if we want to translate legislation files in the airline business, we will see that we actually don't have so many millions of the language pairs for training. So how can we do those kind of low resource cases? It's a very big question. And specifically in this work, we will especially focus on the unsupervised setting. So that means we want to build a model for the target domain. However, in this kind of target domain, we don't have any translation pairs, any annotated data for training. Instead, we have the monolingual data for each of the two languages in the language pair. So this is the unsupervised setting. In order to solve this problem, in order to real train a model that can be performant on this kind of targeted data domain without any data, we need to seek for help from the source domain in the same language pair. And we assume that in the source domain, we have a good amount of translation pairs. And then we have this kind of problems for the unsupervised domain adaptation. So given the source domain of data, and we want to build a good model for the target domain, then how to utilize some methods to transfer the knowledge or information from the source domain to the target domain is the basic and fundamental question in this kind of setting of problem. So this is what is the unsupervised domain adaptation. So after talking about what is the background of the unsupervised domain adaptation for machine translation, I want to further introduce what is the de facto method in this field. So that is the back translation method. So in this kind of method, we are given two data sets, the source domain data set and the target domain data sets. In the source domain data set, we have the annotation, we have the language, we have the parallel translations between the two languages, language A and language B. However, in the target domain, we only have the sentences in each of the language A and language B, but we don't have the corresponding language pairs. So in this case, how to build a model that can translate from the language A to B in the target domain is a question. So let's proceed to the method of the back translation. So we are given the paired language translation corpora in the source domain. Then we can use the annotated data to train a model in the source domain that can translate from the language B to the language A. And then we use this kind of well-trained model to do the inference and translate from the language B to language A in the target domain. Then in this case, we will get the pseudo-paired data that can pair with the language A to B, so that we can formulate a pseudo annotated data or corpora by pairing the translated results and the original sentences in the language B. And then we can use this kind of formulated pseudo corpora to train the model in the target domain that can translate from language A to language B. So in this case, in this way, we can build up such a kind of model that is able to translate from language A to B in the target domain. And reversely, how to build a model that can translate from the language B to A in the target domain, we can follow a very similar way that first we train a model from the language A to B using the data in the source domain, and then do the inference and get the translation results. Then use the translation results to generate or formulate the pseudo-paired data from A to B, and then use this kind of pseudo corpora to train the model in the target domain from B to A. So this is the how the back translation methods can work. It is very simple, but it is experimentally demonstrated to be very, very effective. Okay, so after talking about the background methods or the most standard methods, we proceed to the methods in this work. So by just extending the back translation. So instead of just stop at the one iteration of the back translation, we can actually extend it into many iterations. So previously we have mentioned how to do the back translation in one step. We can denote it as the iteration 0. And next we can proceed to do many iterations. We can have iteration 1, 2, 3, and many, many. So to do that, we can further use the well-trained translation model in the target domain in the iteration 0 to do the translation, so that we can pair the translated results with the original sentences to form a new pseudo corpora. And using this new corpora to further train a model that in the target domain that can translate from language A to B in the iteration 1. And we do the same thing for the other reverse translation direction. Since we can make sure that the translation model that has been trained in the iteration 0 should be better than the translation model that trained using the source domain data, we can make sure that the created pseudo corpora in the iteration 1 should be better, should have the better quality compared with the corpora in the generation 0. And by training the translation model on a better corpora, we can also make sure that the translation models in the iteration 1 should be better than the iteration 0. And by using this kind of assumption, we can also guarantee that we will have a better and a better translation models by doing many, many iterations. So this is the basic idea or the concept of the new method. But so far, we have talking about, say, we do the iterations, and each iteration, we train the translation models on the whole data set. And we also do the translation results and generate a pseudo corpora using the whole data. But instead of doing that, we can make it more efficient. So that is the iterative batch-based back translation.
Sorry, Dee, just reminding you have about like 8 to 10 minutes left.
Okay, okay. I'll be faster. So that means in each iterations, we will draw only a batch of the corpora from the maybe corpus X and implement the step 1 and 2. And also we can draw another batch from the corpus Y and implement the steps 3 and 4. So in this sense, we can do the iterations. In each iteration, we only perform the training batch by batch. So that can make each iteration very efficient. So after talking about the iterative back translation step, based on it, we can add 2 more steps to enhance the model. So the first step is the language modeling step. The language modeling step is performed by doing the denoise autoencoding. That means for the sentences in each language, we can do the corruption to the original sentence and get a corrupted version. And then we train the model to reconstruct from the corrupted sentences to the original sentences by doing the denoise autoencoding. In this sense, we can do the language model. And we do the language model for both languages. So this is the language modeling step. And the next step is about the supervised step. So that means in the iterative back translation step, we use the pseudo corpora to do the translation, to do the training. However, we can also use the supervised data that we have to make sure that to insert into the batch training so that we can make sure the model will not get worse and worse by training the model on the bad translations. And the supervised data we have has 2 tabs. One tab is the source domain dataset, and the other tab is the back translated pseudo corpora in the very first generation. So that is in the iteration 0. We can use these 2 kinds of supervised datasets to train the model. So this is the supervised step. And we combine the 3 steps in many iterations. So overall, for the training procedure, we have n iterations. And for each iteration, we conduct the supervised step, the IBT step, and the language modeling step. And these steps can be shuffled in each iteration, since their order is not that important. So previously we have mentioned and we have described the training procedure, and next we proceed to the models that we have used. So we have used the transformer-based models, which consist of the encoder and decoder. And one thing to note is that for both directions of translations, from language A to B and from language B to A, we share the same architecture, the same model with the 2 directions. And in order to do that, we have a special language embedding to the embeddings of the models. So the language embeddings embeds the language of the source and the target. For example, if we want to translate from language Germany to language German to the language of English, then we set the language embedding of the encoder to German and the language embedding of the decoder to English. So in this way, we can let the model know that what is the translation direction. And another important point is that we initialize our models with the pre-trained parameters, that is pre-trained using a mask language model on a large corpora, such as the a large quantity of the news sentences in the English in both of the languages in the language translation pairs. And next, I want to briefly introduce the datasets we have used. So we try to language pairs, the German to English, and the other is the Romance to the English. And for each of the language pairs, we actually have tried several kinds of specific domain datasets, as well as general domain datasets. For example, the medical, law, and IT and TED can be deemed as the specific domain datasets, and WMT14 is the general domain. So in the last slide, so this slide will introduce what is the main results of our method. So in the second row, marked by the blue line, is the source dataset we have used. And the third row is the target domain dataset we have used. So for the method one, the undoubted method, it is the results from the undoubted setting. That means we train the model, the translation model in the source domain and directly test the performance of that model on the target domain without any kinds of training. Then we come to the setting of the back translation, highlighted by the blue line. We see that compared with the undoubted results, the back translation can give a lot of improvement. And the improvement is even better than many other kinds of methods that have been proposed after the back translation. And next come to our settings. So the setting of IBT is the setting where we only implement the language model step and the IBT step in each iteration without using the supervised step. And we can compare it with the back translation baselines and see that it can improve over the back translation results in, especially for the transfers from between the very specific domain. And then we compare the setting 7 with the setting 6. So setting 7 is the setting where we implement the language model and IBT and also the supervised steps together. And for the supervised step, we use the source datasets as the supervised dataset. And we can compare it with the setting 6 and see that by adding the supervised step can give us some improvement. And next for the setting 8, it is very similar to setting 7, except that we replace the source domain dataset with the back translated dataset in the iteration 0 as the supervised data. And the results show that the performance improvement is actually better than the setting 7. Okay, so here is the summary. So in the previous presentation, I have shown that the transfer learning can be implemented for both the language understanding and also the generation tasks. And as the results show that the performance or improvement brought by the transfer learning can be very obvious and giant. However, we also see that for different tasks, the transfer learning methods can be very different. So in order to implement the transfer learning on a specific task, we need to pick the corresponding method. And in my other works, I have also explored other kinds of transfer learning techniques, such as the adversarial learning and the meta learning onto the sequence labeling problems or the span-based question answering datasets. So finally, I want to conclude that so data scarcity is a very common problem, and especially for those kind of real problems in the industries. And there are a lot of times that we don't have much data or we have very little data to train. And in this case, we can use transfer learning as a very strong solution to those kind of problems, and we can use it as a high priority. Okay, so
Thanks a lot, Dee. So I suggest we unmute and offer a round of applause for Dee for the talk. All right, you can also actually add reactions like applause from your Zoom. So we are almost out of time, but maybe we can take one or two quick questions. Mojde, please go ahead.
Oh, sorry, I didn't have a question.
Oh, okay, Greg? Oh no, Greg also doesn't have a question. Okay. Who has a question? Please raise your hand. All right, so in that case, actually, oh, John, go ahead.
Well, I mean, I'll give it up if anybody else had a question, but so I guess similar to the questions from the last part, did you do any kind of ablative study to see what specifically the changes to the to back translation or the iterative back translation, what you were getting from that you didn't get before?
can you elaborate your question?
So some parts, so blue and up, right? That's a very coarse way of looking at things. Translation got better. And I wondered if you analyzed, you know, what actual, so it's hard to intuit what the iterative back translation is getting you. Are there vocabulary items that, you know, that are unique to the domain that you're getting better now when you went iterative versus just doing a single round of back translation? Or is there something different about the grammar that you're getting? You know, so some kind of qualitative understanding of why doing a back translation, especially when you get this, the problem with back translation is that the target site is good, but the source site isn't. And so the iteration is, it's apparently helpful, but yeah, can you understand what you're getting better?
So I treat the back translation method as a kind of data augmentation. So especially for those kind of domains that don't have data, so we need translation pairs to train a model. And after we build a model that have some capability of translations, we can generate the sentences, the translation results based on the given monolingual data. And in that case, the model can generate good translation results for those kind of say shared knowledge or the shared sentence structures between the source and the target domain. For example, even we for those kind of very specific domains, the language use will be very common between the source domain and the target domain. For example, between the general domain and the very specific medical domain. And those common language use will be shared. So in that case, the translation results can help the target domain by using the back translation.
Okay, thanks.
All right, since we are out of time, so I suggest we stop it here. Let's thank Dee again. And so several of you actually have meetings in the afternoon, so you are free to ask basically any questions that you might have. Thank you, Dee, and we will talk to you again soon.
Okay, thank you.
All right, thanks everyone for coming, and yeah, please follow the schedule and meet with Dee.
Okay.